The question asks how many of these molecules are polar. So we have SO3, OF2, BeCl2, CCl4, and O3. First, let's start with SO3. I went ahead and drew the Lewis structure, and I'm going to explain why I drew it this way in a second. First, let's tally up the total number of valence electrons present in the molecule. So oxygen has 6 valence electrons, and so does sulfur. So let me write that down. There's 6 valence electrons, and then there's 3 oxygen atoms, so we're multiplying by that by 3. Sulfur has 6 valence electrons, and there's only 1. And if you multiply and add that up, you should get 24 valence electrons. And if you count in the molecule, you should get that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you multiply that by 2, you should get 24. So the reason I drew the molecule like this is because oxygen, in terms of formal charge, prefers to have 2 lone pairs and 2 bonds attached to it. So I did that for all the oxygen atoms. And the reason that sulfur has more than 8 electrons around it is it's because it's one of the few elements that can actually violate the octet rule and can, I guess, have more than 8 electrons around it. So next, I'm going to go into the bond dipoles. So first, let's determine which atom is more electronegative. So oxygen has an electronegativity of 3.5, sulfur 2.5. So because oxygen is more electronegative, it's going to have the partial negative charge on it. So let's go ahead and write that down. And sulfur is going to have partial positive because it is less electronegative. So when you're doing bond dipole arrows, you're going to want your arrows to always point towards the more electronegative atom. So because oxygen has the partial negative charge, the arrow is going to be pointing towards it. So let me go ahead and draw these arrows out. Should look something like this. Alright. Next, you're going to want to find the domain and molecular geometry. So the domain geometry is going to be trigonal planar because the central atom has 3 domains on it. So let me go ahead and write that down. And because none of these domains are electron pairs, the molecular geometry is also going to be trigonal planar. So if you actually draw the molecule out, it should look something like this. I'm going to go ahead and redraw the bond dipole arrows. Should get something like this. And because there is equal distribution in the molecule, there is actually no net dipole, which means that this molecule is non-polar. Next is the OF2 molecule, and I went ahead and drew the Lewis structure again. So let's go ahead and make sure this Lewis structure is correct. So oxygen has 6 valence electrons, and there's only 1 of them, plus fluorine has 7 valence electrons, and there is 2 of them. And if you add and multiply this out, you should get 20 valence electrons. So let's go ahead and count around this molecule and see if it's correct. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you multiply that by 2, you should get 20, so that's good. The reason I drew it like this is because fluorine prefers to have, in terms of formal charge again, it prefers to have 3 lone pairs and 1 bond. And oxygen, like I said previously, likes to have 2 lone pairs and 2 bonds. So that's good. Next is the bond dipole. So the electronegativity of fluorine is 4, and on oxygen it's 3.5. So because fluorine is more electronegative, it's going to get the partial negative charge. And oxygen is going to get partial positive because it's less electronegative. And like I said, bond dipole arrows always point towards the more electronegative number. So in this case, or not number, atom. So we're going to go ahead and draw that out. So you should get something that looks like this. Next is the domain and molecular geometry. So if you look at this molecule right here, the domain geometry is going to be tetrahedral because it has 4 domains, 1, 2, 3, 4. But the molecular geometry is going to be bent because of these lone pairs. So if you actually drew out the molecule in a 3D space, it should look something like this. And I'm going to go ahead and redraw the dipole arrows. So if you look at the, this molecule, because the oxygen has lone pairs around it, that means that the distribution in the central atom is going to be uneven. So the net dipole is actually going to be pulling downwards. And because there is a net dipole, the molecule is going to be polar. So the next molecule is BeCl2, and I went ahead and drew the Lewis structure right here. So before we move any further, let's make sure this Lewis structure is drawn correctly. So chlorine has 7 valence electrons, and there's 2 of them. And beryllium has 2 valence electrons, and there's only 1 of them. If you add these and multiply these out, you should get 16 valence electrons. So let's go ahead and count these up in this structure and make sure it's correct. So we have 1, 2, 3, 4, 5, 6, 7, 8 times 2, which is 16, so that works out. So chlorine follows the octet rule, so there's 8 electrons around that, so that's good. Beryllium is different, and it actually violates the octet rule and does not need 8 electrons, which is why I drew it like this. Okay, so next is the bond dipole arrows. So beryllium has an electronegativity of 1.5 and chlorine of 3.0. So because chlorine is more electronegative, it's going to have the partial negative charge. And beryllium is going to have the partial positive because it is less electronegative. Let's go ahead and draw the dipole arrows. So remember, the arrow always points towards the atom with the partial negative charge. So that's what we're doing here. So you should get something that looks like this. Sorry, like this. Next, let's find the domain and molecular geometry. So domain geometry is going to be linear because it only has 2 domains, 1, 2. Molecular geometry is going to be the same because none of these domains are actually lone pairs, so it just stays linear. So if you were to draw this out, it looks something like this. Go ahead and redraw the dipole arrows. Alright. So if you were to look at this picture, none of these domains are actually lone pairs. So these forces are pulling in opposite directions, and they actually cancel each other out, which means that there is no net dipole. And because there is no net dipole, that means that this molecule is actually non-polar. The next molecule is CCl4. Here's its Lewis structure. So let's make sure the number of electrons is the same as the picture. So chlorine has 7 valence electrons, and there are 4 chlorine atoms, so we're going to multiply that by 4. Carbon has 4 valence electrons, and there's only one of them, so we're going to multiply that by 1. If you multiply and add this up, you should get 32 valence electrons. So let's count this and make sure this is correct. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 times 2 is 32, so that checks out. The reason I drew the structure like this is because, again, for formal charge, chlorine likes to have 3 lone pairs around it with 1 bond, and carbon likes to have 4 bonds and no lone pairs. So that's why I drew it like this. Next, let's find the bond dipole arrows. So carbon has an electronegativity of 2.5, and chlorine has one of 3.0. So chlorine is actually more electronegative, so that's going to have, chlorine atoms are going to have the partial negative charge. And carbon's going to have the partial positive. And let's draw the arrows. Arrows, again, always point towards the more electronegative atom. Should be 4 arrows. So you should get something that kind of looks like this. Next, let's find the domain in molecular geometry. So domain geometry is going to be tetrahedral because there's 4 domains around the central carbon atom. And the molecular geometry is also going to be tetrahedral because none of these domains are actually lone pairs. So if you drew this in a 3D space, it should look something like this. Like that. And let's go ahead and redraw the arrows. So because none of the domains around the carbon atom are lone pairs, the arrows all pull in the same direction and they all cancel out. There is actually no net dipole, meaning that the molecule is non-polar. The final molecule is the O3 molecule. Here's the Lewis structure that I came up with. So before we move any further, let's make sure this structure is actually correct. So oxygen has 6 valence electrons, and there's 3 of them, 3 oxygen atoms. So 6 times 3 is 18 valence electrons. So let's go ahead and count and make sure that's correct. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Times 2 is 18, so that works out. This Lewis structure is different from the others because it actually has resonance and can be drawn in this way as well. So if you drew either of these structures, both of these would be correct. So if you actually think about it, the bonds between these oxygen atoms would actually be 1.5 and not 2 and 1. Okay, next let's go into the bond dipole arrows. So they're all oxygen, and the electronegativity of oxygen is at 3.5. And because they're all 3.5, there's actually surprisingly no dipole arrows, which is very interesting. So let's go ahead and move on to the domain geometry in that case. So the domain geometry is trigonal planar because there's 3 domains. You have 2 oxygens and the lone pair. And the molecular geometry is actually going to be bent due to the electron lone pair. So if you were to draw this out in a 3D space, it would look something like this. I bet you're wondering, because there is no dipole arrows drawn up here, there is no net dipole movement at all, which means it is nonpolar. But that's incorrect. Because these 2 oxygens have more electron pairs, as you can see up here, these are actually going to be given the partial negative charge. And this oxygen right here only has 1 lone pair, so it's going to be given partial positive charge. So the actual arrows are going to be drawn like this. And because there is 3 domains and one of them is a lone pair, and these forces don't actually cancel each other out, it's pulling, the net dipole movement should be pulling downwards. So because there actually is net dipole, the molecule is considered polar. One of the most common mistakes is that students draw the Lewis structure with the dipole arrows and consider themselves done, but that's not actually true. You have to draw the molecular geometry as well. So if you completely disregard this picture right here and just look at this, it looks like there's a net dipole going up like this, which would mean it was polar, but this molecule is not polar. You actually have to draw out the molecular geometry, which looks like this, trigonal planar. And if you look at this picture, this actually will tell you the polarity. So it's actually nonpolar because there is no net dipole movement.